All right. A growth or a decay model? Growth. Good. At that point, you know you're picking 0 and 1. What am I plugging them into? What's my base graph? 2 to the x. Perfect. So 2 to the 0 is? And 2 to the first, 2. What do I have to multiply those y values by? Good. So 0 and 1 stay there, but now I take 2 times 1, 2 times 2. So here are the points, 0, 2, and 1, 4, that I am then going to move where? Good. Left 3, down 1. Where did my asymptote start out being? Y equals 0. So remember, when we graph, our asymptote's also going to move down 1. Okay, so if I just show you what the base graph looks like, 0, 1, 1, 2, it's growth. There's my base. I'm going to take 0, 2, and 1, 4, and move those points left 3, down 1. So I go left 3, down 1, left 3, down 1. My asymptote also moved down 1. So my asymptote is down here now. So my graph comes up through those 2 points, getting closer and closer to that line. What's my asymptote equation? Y is equal to -1. What is my domain? Perfect. And what is my range? Perfect. Remember that your asymptote and your range are going to have the same value. Asymptote is always equal to, range is either going to be greater than or less than, depending on whether or not that graph flipped. Good? Questions there at all? All right, what about this one? Growth or decay? Decay, good. What happens to this decay graph? It flips. Remember, the actual process takes care of where the numbers are going to be, but what does a decay flipped look like? Decay looks like this. If I flip it over that x-axis, we're going to connect it like that one. So this is how you're going to connect your points, is with that shape. Okay, so you got to remember flipping it's over the x-axis. All right, so my decay graph, I plug in 0 and -1 because -1 gives me the easier value to graph. When I plug into what? 1/4. Perfect. So 1/4 to the 0. What's 1/4 to the -1? Perfect. All right, so then I take those values. Before I go any further, the asymptote's at 0. Good. Remember, asymptote always starts at 0. I'm taking those points, the 0 and the -1 stay, but we're going to multiply the y's by -3. Okay, so -3 times 1, -3 times 4. -3 and -12. Where am I moving that? Good. Right, 1. Up 3. So again, I'm going to show you where the base graph is. 0, 1, -1, 4. So there's my base, but remember that's flipping over the x-axis. So when I go to 0, -3, and -1, 12, it doesn't look like a decay graph anymore. It looks like it's in the wrong spots. But you remember you're going over that x-axis. I'm moving right 1 up 3. So right 1 up 3, right 1 up 3. Where's my asymptote now? +3. So I take those points and I come up and get closer to that x-axis. Where is my asymptote? Equation-wise? Good. My domain and my range. Perfect. Always got to look at where's that graph located. All my y values are smaller than my asymptote. Yeah. Say it again for me. Up here. That's what's moving us right and left. So because the variable is now my exponent, the exponent's going to have an expression in it rather than just a value. Whatever's with your x moves you right and left. Good? Better? Okay. So then what we do today is actually apply these exponential growth and decay. So when we graphed it, now we want to know why would we even use it. So from 1990 to 2000, the population of California can be modeled by P equals 29,816,591 times 1.0128 to the T, where T is the number of years since 1990. Identify the population in 1990, in other words, our initial amount, the growth factor, and the percent increase. When we did this, we just did it off of a basic equation and said, what's my A value, what's my B value? Well, now I want to know it in terms of this problem. So what's the population in 1990? So you got 29,816,591 people. What's the growth factor? The growth factor itself is the decimal. As a percent, you're right, it's 101.28, which is going to help us find our percent increase. So if it's 101.28%, how different is that from 100%? There's my percent increase, is the 1.28%. So the growth factor is just purely your B value. Remember, this is in y equals a times b to the x form. The B value, the thing that's being taken to the power, is your growth or your decay factor. A is your initial. Percent increase or decrease is how different is it from 100%. So you have to change your growth factor or decay factor to a percent, then figure out the difference between that and 100. Good? Okay. So a company purchases a piece of equipment for its assembly line. The value of the equipment depreciates at a rate modeled by y equals 175,000 times 0.72 to the t. Identify the initial amount paid for the equipment, the decay factor, and the percent decrease. So what's the initial amount paid for the equipment? Absolutely. $175,000. What's my decay factor? 0.72. Percent decrease. Yep. 100% minus that 72%, 28%. Now, would I necessarily need to see that percent subtraction? No. If you can do 100 minus 72 in your head and just write down 28%, that's all good. So when I look at the equations, how do I know growth versus decay? When it's greater than 1, what is it? Say it again, I'm sorry. Increase. So it's a growth. What number do I look at for that? Which value, A, B, or X? B. It's the number being taken to the power is greater than 1. It's growth. When it's between 0 and 1, decay. So it's always your B value, your growth or your decay factor. Greater than 1, growth, less than 1, or between 0 and 1, decay. Something sometimes people say is that it's whenever it's a fraction, it's decay. Remember, there are fractions bigger than 1. 3/2 is 1.5. It's bigger than 1. It's growth. So you have to make sure you look at what the fraction is. It's got to be a fraction between 0 and 1 to be decay. Good? Because now we're going to write. In 1996, there were 2,573 computer viruses and other computer security incidences. During the next 7 years, the number of incidents increased by about 92% each year. Write the exponential function that describes that situation. So what's our A value? What's our initial value? Absolutely. Okay. How am I going to get my B value? Am I increasing or am I decreasing? Increasing. So I know it's growth. It's a growth of 92%. What am I going to do to get my B value? Absolutely. 100 plus 92 gives me 192%, but my B value then is going to be perfect. You got to change it to a decimal. So 1.92. Okay, we've got to define some variables here. I know my A value, I know my B value, but there's got to be an X and a Y kind of thing going on. What do you want your variable to be? It's going to be the number of years. So what's your variable that you want to use for number of years? X. Now this model is only from 1996, right? So it's not just the number of years, it's the number of years since 1996. We can't use any of the other years, so when we go to plug numbers into our formula, we always got to remember it's since 1996 happened, because that's when our initial value was. What do you want to use for your other variable? Yep. I'm going to put it computer security incidents, just because it's viruses and other stuff. Okay, so what does Y equal? What's my A value? Yep. And what's my B value? And it's going to go to the X power. So when I then want to use my function to predict the number of computer security issues in 2004, what do I need to know? How many years it is since 1996? So how far is it between 2004 and 1996? So what do I do to figure out my number of computer issues? Correct. So what do we got? Yep. It comes out as 0.659. I would take it either way on rounding for this. If you round technically rounding, you'd say 4,775 and 171. You just put the word about by there, and I don't care which way you round these because it's really just an estimate of how many issues you're going to have. But you can't have 0.659 of an issue or an incident. It's either an incident or it's not. So you got to round one way or the other. I am good with whichever way you do it. Good? All right, let's write one more. You buy a new computer and accessories for $1,200. The value of the computer decreases by 30% each year. Write an exponential model giving the computer's value V in dollars after T years. So they already defined our value or our variables for us. V is the value in dollars. T is your number of years. They didn't give us a starting year. They just said in years because all you're buying it and then it's the number of years since you bought it. You're not going to write years since you bought it. Okay? What is my A value? What's my initial? Good. Growth or decay? Decay. Good. So now I need to decay by 30%. 70. Perfect. 100 minus 30 gives you the 70%. What is my B value then? 0.7. Good. You always change that percent into a decimal. All right, so V is going to equal what? A value? Perfect. That was write the exponential model. Now it says, what's the value after 4 years? What do I do? Perfect. So what is its value after 4 years? Yep. Dealing with money, around to the 100th. So sometimes you have exponential growth and decay that are as simple as that. Another location growth and decay are used, mostly growth, is banking. Banking, you have two different kinds of interest. You could have simple interest, compound interest, and then we'll deal with a third type of interest in the next section. Simple interest is interest paid only on the initial principal. So the amount that you put in, nothing else. So if I put $100 in my bank account, simple interest would say whenever it's calculating that interest, it's only calculating it on the 100 that I put in to start with. Compound interest is interest paid on that initial principal and the previously earned interest. So I put that 100 in. The first year it's calculated and I make $10. Now I have 110 in there. The next year it calculates the interest on the 110, adds that in. The next year it calculates the interest on the 100 and whatever. Just keeps adding in to get to your total of what's in there now. Now I'm calculating it based on that. When you do compound interest, there is a formula. A equals P times parentheses 1 plus R over N to the NT, where A is the balance in the account. If you want to consider it your ending amount. Not necessarily that you stop the account, but you want to know what is it at this point. That's where I'm stopping my calculation. What's my ending? P is the principal. That's your starting amount. How much did I put in initially? R is your interest rate. That's always calculated as a decimal. Then you've got N is your number of times compounded in 1 year, and T is the number of years. N will be stated to you not in terms of saying N equals this. They'll use words like it's compounded annually. How many times in 1 year is it compounded if it's compounded annually? Once. What about semi-annually? Every 6 months, so 2 times a year. Semi-annually, biannually mean the same thing in terms of this formula. Okay, quarterly. 4, good. Monthly. Daily. Absolutely. Okay, so just some numbers I wanted to make sure you had in your head for the values used. Okay. Good. All right, so Assume $1,000 deposited in an account that pays 8% annual interest, compounded quarterly. What's the balance after 1 year? So which one am I looking for? A, P, R, N, or T? A. What is the balance? That's my A value. So I don't know that, but I do know P. What did we put in? What's its principal? 1,000. What is R? The number of time, or sorry, the interest rate. 0.08. Remember, it's 8%. You need to change it to a decimal. N, the number of times compounded in a year. 4, because it's quarterly. And then how many years are we dealing with? Perfect. So A equals P is 1,000. 1 plus R is 0.08 over N, which is 4, to the power of 4 times 1. You can type that whole thing in your calculator. If you are typing the power in as the formula rather than multiplying the 4 times the 1, make sure that you put parentheses around it, because if you don't, it will not calculate it correctly. If you want to do it in parts, you can do it in parts. I don't really care which way you use your calculator. I'm good with seeing it, the numbers plugged into the formula, and giving me an answer back. We're dealing with money, so what are you going to round to? Hundredth. Perfect. So what do we get back? Absolutely. All right, assume 5,000 is deposited in an account that pays 6% annual interest. Find the balance after 25 years if the interest is compounded quarterly. So we're going to write down the information on this, and I'm going to have half of you calculate one, half of you calculate the other. So what's my A, or my balance? Do I know it? What's P? What's R? What's N for this part A? Good. What about T? 25. Okay. Other side, when it's compounded monthly, what's the only thing that changes? N value is 12. Everything else is the same. Okay, so these 3 rows over here, calculate part A. You 3 rows over there, calculate part B. So plug your numbers in, and then type it in the calculator and figure out what our values are. Again, if you're not multiplying 4 times 25 in parentheses, 12 times 25 in parentheses. If you're going to multiply it first and then type it in, that's fine too. Just make sure that you're using parentheses if you do not. All right, what do we got for the compounded quarterly? Perfect. What about monthly? Perfect. So the more times you compound it, what happens? More money. So from your standpoint, you want to get an account that compounds more often because you want to add that money in. Why? Because every time it's compounding, it's multiplying something times a bigger balance. So after 1 month, it's going to add that money in, and then it's going to calculate the next time off of that new total. So each time you're getting a bigger dollar amount back, the more often you compound. Good? All right, the last one, we're going to have something new missing. How much must you deposit in an account that pays 6.5% interest compounded semi-annually to have a balance of $5,000 in 15 years? What do I know now? A, absolutely. Balance of 5,000, that's my ending amount. Okay, what am I missing? P, how much must you deposit? Okay, R is? N is? Good, semi-annually. And then T. Okay, so when we plug this in now, we're going to have to do a little bit different. You can't just type it and come back with your answer because now it's P that's missing. Okay, depends on how good you are typing your calculator. At this point, if you want to just recognize, I have to divide by this whole chunk. You can do that. You can just go over to your calculator and divide by it. If you are not particularly good at manipulating your calculator, you might want to calculate out what is 1 plus 0.065 over 2 to the 30th power and get a value there. I would not take it to the 30th power because the 30th power is going to make this a really big long decimal, which is going to be a pain to try and type in. So if you just type in what's here, you would get back 1.0325. So if it's easier for you to type in 5,000 divided by 1.0325 to the 30th, go ahead. If you can type the whole thing in from the start, go ahead. It's how good you are at your calculator and what your calculator is capable of doing. My goal is usually when I'm doing something like this to not round unless I have to. So my goal would be to put it all in at once so that I'm just rounding the final answer. What do you get back? How much? Perfect. So if you're not getting the numbers we got for our values back out of the calculator, while you're copying down the homework, raise your hand for me and I'll come figure out what's going wrong in the calculator. But your homework is on page 482, 25, 28 to 30, 35 only part A, 37 A and B, 38 A and B, 39 A, and 43. And then on 489, 26, 30A, and 31A. So only do the parts that are mentioned there. Don't do the whole problem. And it's growth and decay, so that's why we're still doing it on the 2 different pages.